So in this video, we're going to talk about rotating graphs, 2D graphs, in 3D space, and then finding the volume of those graphs. And so this is a topic that requires calculus and integration, and it's actually a pretty fun thing to do once you get the hang of it. However, a lot of teachers who cover this don't really cover how to do it and why it works, and they don't give you the intuitive understanding of how we even realized that this was a problem that should be solved using integration. So that's my goal for this video. But first of all, let's just start with the basics. Imagine we have a graph here. And this is, you got your x and your y-axis, of course. And let's say we have this graph here. We have a sideways parabola. Sorry for my lack of drawing skills. And if you'll remember from your Algebra 2 class, this usually comes in the form y equals x, or sorry, x equals y squared. And so then the question is, what if we were to take this and revolve it around this x-axis? And at first, this is going to be a very difficult thing to sort of conceptualize in your head. But it's really important that you are able to conceptualize it. So if we were to rotate this around x-axis, so about x-axis, we would get a graph that looks something more like this. And this would be all circular like that. If you're really not seeing this in your head, I recommend you take a moment, pause this video, and sort of think about it. What would happen if you took this sheet, imagine this sort of as a sheet, right? And if you just rotate it around this way, around this x-axis here. And as you're rotating it, you sort of drew everything in between. What I'm saying is you sort of made it a solid object. And then you would essentially get this sort of figure. And if you were to turn this figure upright, if you turned it sort of 90 degrees, you'll get sort of a vase-like figure that looks like this, maybe a bit more pointy. And, it's something like a cup that's filled in, or maybe you're thinking of more like a vase, right, with flowers in it. If you want to draw, I'm sorry about my drawing skills, but you put some flowers in it. That's sort of the thing you would get. Except vases have a hole in them where the flowers go and the water goes, right? But in this case, we're going to assume that this does not have any water in it, and it's just a completely solid object. So, now that we've sort of imagined this figure that we've rotated around the x-axis, let's try to figure out how we can find the volume of this object. And it's important to recognize that this is going to be volume that we're looking for, not area, because it's a 3D object. Okay, so let's think about this logically. If we remember from just normal integral calculus, 2D calculus, we'll remember that when we have these graphs, what we were doing is we're splitting these into rectangles of very small width, a width that we call dx. This right here is of width dx. And we were trying to make this dx, and we were using these rectangles to approximate the area of this, but we were saying as these dx's got closer and closer to 0, and as the number of rectangles we have go closer and closer to infinity, we are actually going to get the exact result of the area under the graph. And so let's see if we can do a similar thing here. What if instead of splitting this into rectangles, we were to split this this 3D object? Remember, think about it in 3D space, rotate around the x-axis. If we were to cut slices into it that look like this, let me see if I can do that a bit better. but these circular sort of slices that are basically forming a disk, we could use these disks to approximate the area. Because if we're able to find the volume of one of these disks, then we can integrate it essentially and get the volume of this entire object. And so, similar to how we did it previously, what we can do is make these disks here that are super duper small in terms of their size. So my drawing abilities are not great, but here's our disk. Think of it like a CD or something, just a few millimeters thick. And we're going to call this thickness that we have, this should be touching this axis here, this thickness, we're going to call that dx. And so let's think about how can we find this volume of just one of these disks. And what you can do is just think about the formulas you learned in your geometry classes, which is that you take the base and you multiply it by the height. In this example, the base will just be pi r squared. We'll figure out r in a second, and then we'll be multiplying it by the height. And first of all, we've established that the height of this cylinder, actually, it's a disk, but the more geometric term for it would be to say cylinder, because disks sometimes imply that it doesn't really have a thickness to it, and this does have a thickness to it. So h is going to be dx. So we're going to have pi r squared dx in replacement of h. But then also we have to figure out this r variable. Pi is, of course, a constant, but r shouldn't be too difficult to figure out either. R is this length here. It's just however long it is from this center to any of these points out here. And if we look at it in terms of this exact r, what we'll find is that this here, this distance here, is actually r, as with this distance as well, because in terms of just this distance between the two sides of this sideways parabola, that would be the diameter, right? And half of the diameter is the radius, which is either of these two sides, because we know, based on this graph here, that this length here, this r, is equal to this r. And so we can take just this height here at any point as r. And how do we get the height? Well, the height is just whatever y is at any point. So if we take this equation and we solve for y, we get y equals the square root of x. So what this tells us is that any value x along this, we're going to have a height here of root x, which is going to be our radius. So we'll go ahead and plug that in as well into our equation, and then we get pi square root of x squared times dx. We can simplify this down a little bit, pi x dx. Okay, so at this point we have the volume of just one of these small slivers of dx height, or dx thickness, right? And so at this point, we need to figure out the total volume. And so let's say the total volume of this would obviously be infinite, because this continues on forever. So let's say we were to take the volume from this point at x equals 0, and we were to take it to this point, and where x is equal to 4. So we want to find the volume in that region. And using this, we can use these principles that we were talking about earlier, right here, which is we want dx to go to 0. Because as dx goes to 0, if we have a bunch of these cylinders here that we're sort of separating this into, as dx goes to 0, our approximation of the area at one particular section gets more and more accurate. This dx here is obviously making some sort of assumptions, because generally, if you have a cylinder, this side here needs to be parallel to this side, right? It can't be increasing at one point, and the radius needs to stay the same. However, in this, we sort of have a radius that's increasing. So as we bring dx closer to 0, we're going to get a more accurate representation of the volume of this particular cylinder. And then as we increase the amount of cylinders we have to infinity, we get a better approximation, thus, of the actual area that's in here. And what did we use to make both of these things happen in the past? We would use an integral. An integral does all of that for us. And in this case, an integral will do the same thing. So what we can do is take this equation we have and integrate it along or just pop this into an integral essentially. And so this becomes pi x dx. And the bounds on this are going to be from 0 to 4. That's what we want it to be adding up. And we can obviously take out this pi because it's a constant. So this becomes x dx, 0 to 4. And fortunately, we're in a scenario where we don't really have to worry about integrating this because this is a simple thing to integrate. So this just comes out to pi x squared over 2. We're evaluating that from 0 to 4, of course, and that's getting us 16 up here, 16 over 2, 8 pi minus 0. That comes out to 8 pi. And with that, we have our final answer. The total volume of this sideways parabola here, when it's rotated about the x-axis, is going to be 8 pi. And remember that this would be units cubed because this is volume. This is not area. It's volume, of course. So with that, let me know if you have any questions in the comments below, and thanks for watching.